Hello, my name is Jeffrey, and this is my video lab report for Physics 2211M, lab number 1. To introduce this lab, let's first analyze its purpose, its models and fundamental principles, and the main result. The purpose of this lab is to apply Newton's second law, aka the momentum principle, to observe the properties of an object with constant velocity in real life and in computational modeling, and to graphically analyze the position versus time of an object with constant velocity. Because this lab is all about a moving object, it's important to apply Newton's laws of motion. In particular, this lab tests Newton's first law, which states that objects at rest tend to stay at rest, and objects in motion tend to stay in motion unless some external force acts upon it. Furthermore, to predict the object's motion, we need to know the net force acting upon it, its velocity, and its position at regular intervals or time steps. Newton's second law reveals the object's net force, as it states F net equals ma equals m delta v over delta t equals delta p over delta t. Free body diagrams, such as the example shown to the right, can be used to illustrate the net force. In this case, since we assume the object has constant velocity, delta v equals 0, meaning F net must also be 0. Note that this doesn't mean that there are no forces acting upon the object. Rather, all the combined forces cancel each other out. For example, the gravitational force exerted downward on the object is opposed by the normal force with the same magnitude in the opposite direction. These equal and opposite forces exemplify Newton's third law, which states that every action has an equal and opposite reaction. Once we know F net, we can plug it into the velocity update formula, v final equals v initial plus F net over m times delta t. And in general, once v initial and v final are known, both values can then be used in the position update formula, r final equals r initial plus v average times delta t. As for the main results, the observational data and the computational model were very similar. In both datasets, the position increased in roughly equal intervals for each time step. However, the observed data has slight inconsistencies due to potential sources of error. For my observational data, I used a water bottle as a system, with the earth and the table the ball rolled upon as its surroundings. I chose a bottle to minimize friction, since friction would create force in the x direction and cause non-constant velocity. The initial conditions of the bottle are that it's placed at the origin at t equals 0 seconds, and it is assumed that it moves at constant velocity along the plus x axis. Therefore, it has no velocity in the y or z direction, and it has no acceleration. In equation 4, this can be expressed as v equals v sub x 0, 0 meters per second, and delta v equals 0 meters per second. Once I recorded my video, I uploaded the video to Tracker, with the reference measurement being the ball's diameter of 17 centimeters. I also made the x-axis go through the diameter of the bottle, and the y-axis tangent to the leftmost point of the bottle in the beginning of the video. However, I had to tilt the axis 1 degree from the horizontal to account for the camera being placed slightly unevenly due to my phone case. I then assigned the bottle as a point mass, and manually selected its leftmost point at each time step to gather the position data, as shown to the right. For my computational model, I modified the GlowScript template to correlate with my observational data. I edited the object radius, the initial ball devel vector, the delta t variable, the parameter for the while loop, and the ball deposition vector update within the while loop. I also changed the print statement to print data that I could paste into a spreadsheet. This is what the output of the program looks like. Note that the position versus time graph is positive, constant, and linear, while the velocity versus time graph has a slope of 0. Both of these indicate constant velocity. Here's the data from both Tracker and GlowScript pasted into the same spreadsheet. Both datasets have the same number of time steps, average position update, and average velocity update. So the line graph comparing the two in the upper right shows they have very similar slopes for position versus time. However, the observed data does slightly deviate from the constant slope from the simulation data. This difference can be attributed to several sources of error, including camera lens distortion, unevenness from the surface the camera was resting upon, camera vibrations as the ball rolled on the table, motion blur from the bottle, making its edges unclear, human error from manually placing the tracking points, slight friction between the bottle and the table, and slight unevenness from the table surface. In addition, there could also be rounding values derived from the tracking for the computational model. Now, if the axes were flipped, the magnitudes of the position and the velocity at each time step would be the same, but both would be in the negative x direction. The position versus time graph would have a negative slope, as shown in the bottom right, and the velocity versus time graph would have a constant slope below the x-axis. In equation form, this would be expressed as v equals negative v sub x 0, 0 meters per second, and delta v equals 0 meters per second still. So in conclusion, what does this all mean? Well, Newton's first law still applies, as the ball in motion did stay in motion. The constant velocity in the x direction indicated that F net in the x direction equals 0, according to Newton's second law. The ball had no velocity in the y direction, since the normal force equals the gravitational force as an application of Newton's third law, so F net in the y direction also equals 0. And assuming there's no velocity in the z direction, so the ball doesn't get closer or further from the camera, F net in the z direction equals 0. Therefore, F net in general just equals 0. And because of that, we can assume that v final equals v initial for each time step according to the velocity update formula. And using the position update formula, V average equals V final, which also equals V initial. So the ball's position increases a constant amount for each time step.